A sneeze, a runny nose, a little fever. When a virus pays a visit, it raises questions about the future and the past. How long will it last? How and when did I get infected? In fact, both types of questions are usually linked. Knowing how we caught a disease can help us avoid spreading it. But reconstructing the past is far from easy. For any scientist, this means carrying out an investigation while missing some crucial information. Let's take an easy example. Several people start from the same place and walk in straight lines in different directions at the same speed. Let's try to determine the starting point using only two pieces of information: their end position and the distance they walked. We can draw, for each final position, a circle whose diameter is equal to the distance that each person walked. We know that for each person, the starting point must be on this circle, and that everyone has the same starting point. With only one person, we lack information. With two people, we can identify two possible starting points, where the circles cross each other. One of them is a starting point, but we do not know which one. We still do not have enough information. With three people, there is only one intersection between the circles, and we can identify the starting point with certainty. The more information we have, the easier it is to reconstruct the past. Below a certain threshold, we have to make hypotheses, and we cannot be sure of their validity. This threshold depends on the complexity of the story we are trying to reconstruct. Let's change the rule of our example, this time not asking the people to walk at the same speed, but allowing each person to choose their own pace between a known maximum and minimum value. Even if we know the final position of each person, it is impossible to know for sure how far they walked. Our precise circles are replaced by two circles, one being the minimal distance, the other the maximal distance. The starting point must be somewhere in between the two, in the intermediate zone. This time, three participants will not be sufficient to identify the starting point of the group. We will need much more information to get a more precise idea of the origin. Whatever the question we try to answer, there are two levels to get a precise reconstruction of the past. First, having a lot of data, and second, knowing as much as possible about the process. The more complex or poorly understood the process is, the more data you will need to be able to form a reasonable hypothesis. We could make our example more complex by adding barriers or by no longer restricting people to walk in straight lines. But even then, it would be much easier than most of the past events that scientists try to reconstruct. Scientists rarely have enough data to perfectly reconstruct history. They have to make some assumptions and end up formulating what we call a model, a possible scenario corresponding to known information, but probably simplified compared to reality. Scientists can use mathematical tools to assess the reliability of their model. They are also interested in correcting or strengthening it if they get new data. This general principle of constructing an explicative model for more or less complete data corresponds to many situations. In our previous example, we were interested in the movement of a group of people. Let's now consider that instead of walking, they talk to each other. One of them tells another one a message. Then, this person tells what he understood of that message to others, and so on. Let's consider a group of people where one person tells what he understood of a message to someone else, and so on. Each time, that person might introduce some modifications or errors. Without being part of the initial group, we can try to reconstruct the history of the message and how it progressively changed. First, we will need to collect messages from some of our participants. All would be slightly different versions of the same original message. We then compare all of these gathered versions. It seems reasonable that the variants that have fewer differences are probably more recently linked. This can help us building a family tree of the message. It links together all the messages that we know have a common origin, with some unknown intermediate versions between them. These two may have heard the message from the same participant, which himself heard another version from another participant higher in the communication chain. We can estimate the differences between these intermediate steps and represent them as the length of the branches in our tree. We also know at which moment each message has been sampled. By comparing the number of differences between several closely related versions, and by looking at the elapsed time between the sampling of these messages, one can estimate the rate at which a message changes. This rate, or clock, can then be used to infer the time between any two different versions of the message, as well as the time of the whole process. If this example of the evolution of a message reminds you of the evolution of biological entities, it is not a coincidence. As explained in the first episode of Varevo, genomes are themselves messages that change over time. The principles represented here in this second episode are the ones scientists use to reconstruct species evolution. How can we combine everything to study how viral epidemics spread? Stay tuned for the next episode of Varevo.